So in order to avoid the discontinuous conduction of mode, the current from the current from the inductor should never become zero. Therefore we are using the same condition, delta IL, the ripple from this inductor should be less than or equal to 2 times the average value of the current from this inductor. So I will use either value of delta IL. I am using the value of delta IL during the charging time because it is simple expression. So KVS over FL is equal to 2 times I naught over 1 minus K. I naught over 1 minus K is the average value of the inductor. Okay, so if I put this value, Vs is equal to 1 minus K times V naught, then I will get K into 1 minus K times V naught. This value has come in place of this term, is equal to 2 times the same expression that was on this side. K into 1 minus K whole square, this will come over here, the cross multiplication takes place, and K into 1 minus K whole square times V naught, this 2 will come over here, 2 F I naught is equal to inductor. So this should be left over here, but if we want to further simplify it, V naught over I naught is equal to load resistance. So this is the critical value of the inductor that I need in order to avoid the discontinuous conduction mode. If I am given a range that the output current may vary from 1 to 10 ampere, in that case I will always design the inductor on the base of lower for the lower current in order to avoid the discontinuous conduction mode. Now I have to calculate the capacitor. The capacitor waveform is like this. When we were talking about the first mode, when the switch was in operating condition, the diode was out of circuit. This capacitor was supplying current to the load. So the current at this point is 0. Since this is in reverse bias condition, no current is flowing from the source side to this side. In that case, you can say that this is dividing into two paths. This is capacitor current and this is load current. 0 is equal to load current plus capacitor current. So capacitor current is equal to minus load current. This is why during the time period 0 to kT, when the switch was on, the waveform is minus I load current, like this. So delta Q is equal to C delta V naught. Delta Q is the area, which is equal to I naught current, means the output current or the load current, and the time is kT, so I naught into kT is equal to C delta V naught. Okay, now if you want to calculate this output ripple, if you are given the value of capacitor, or if you want to calculate the value of the other quantity, you can use this formula. Either you will be known this capacitor value or this output voltage ripple. That is, either it is given to you that design a capacitor such that at output you only receive 1% ripple or 2% ripple. So one scenario is this, and in other scenario can be that you are given a capacitor of some x microfarad, and you are asked to calculate this ripple that will appear at output. This is the summary of our today's lecture, in which I have written the same values that we have calculated in our lecture.